Okay, to start Unit 8, we're going to start talking about polygons with a quick review and angle measures. So your objectives today are identify, name, and describe polygons, and then use the sum of the interior and exterior angles of a polygon to solve for angles in a polygon. So, as a quick review, polygons, remember that they have sides that are segments and points that are called vertices. There are no curves, and we name polygons according to the number of vertices or the number of sides that a polygon has. You can name a polygon by listing its vertices consecutively, either clockwise or counterclockwise. So if we look at this first example, this has 1, 2, 3, 4, 5 vertices, meaning it's a pentagon. Our next figure is not a polygon. It's obviously a circle, but because it has curved sides, circles are not polygons. The star figure is a polygon, and we can name it according to its vertices as well. Don't forget to include vertices that go in towards the polygon because this polygon is concave. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 vertices or sides, making this a decagon. Polygons can be classified as convex and concave. We've talked about this before. Remember, convex means that all the sides, when they're extended, they extend outside of the polygon, whereas a concave polygon is when you extend a side, like on this arrow, the extension of the side goes through the polygon. When we start looking at the measures of the interior angles, we're only going to be talking about convex polygons. So this first polygon on the left is convex. It is a convex 1, 2, 3, 4, 5 pentagon. Our next polygon is also convex, and it is a convex quadrilateral. Quadrilateral is the most generic name for a four-sided polygon. Our next polygon is a 1, 2, 3, 4, 5, 6, 7 heptagon or septagon. But as we discussed already, the sides when they're extended go in towards the polygon, so this is concave. We already know that the star is a decagon, and as we extend any of the sides, we can see that it goes through the polygon, making that concave as well. Finally, we have a concave 1, 2, 3, 4, 5 pentagon. All right. Remember that regular polygons mean that they are equilateral and equiangular, meaning that all of the angles are congruent in a polygon as well as all of the sides. So this equilateral quadrilateral has another name called a square. We have an equilateral triangle here that could also be described as equiangular, an equilateral pentagon, and an equiangular pentagon, so we'll call that a regular pentagon, as well as a regular hexagon here. So what we're going to be looking for are the measures of angles in regular polygons in just a few minutes. Another reminder about polygons: when you're naming them, you're going to name them by the number of sides. So take a quick look at this list and refamiliarize yourself with the names of the different kinds of polygons. Remember that a septagon and a heptagon are interchangeable. And when we look at an n-sided figure, like a 13-sided figure, we can call that a 13gon, for example. Okay, so here's the new information. We want to look at the sum of the interior angles of convex polygons. Whether they are regular or not, they follow the same rule. So let's start with what is the sum of the interior angles of a triangle? We've talked about this several times in class, and we know that all three angles of a triangle add up to 180 degrees. So if that's our baseline of information, can we use that for other polygons? What we want to do is look at the minimum number of triangles in a polygon that contains all sides. So what is the smallest number of diagonals I can draw in that quadrilateral so that I have all sides contained in triangles? So if I draw one diagonal, I can have one triangle here and a second triangle here. As you can see, all the sides are contained in these triangles. They're all included in the angles. Well, we know the measure of each triangle is 180 degrees. So what's the total sum of the interior angles of a quadrilateral that is convex is 360 every time. As long as that quadrilateral is convex, it is 360 degrees. So let's look at a pentagon. We have one triangle here, one triangle here, and that leaves us with our last triangle here. So the minimum number of triangles we can draw to include all sides of this pentagon is 3. We know each triangle has a sum of 180 degrees, which means that the total sum of interior angles on our pentagon, any pentagon as long as it's convex, is 180 plus 180 plus 180 degrees, or 540 degrees. Finally, what about a hexagon? So let's go ahead and start with our minimum number of triangles. A triangle here, 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 and here. Okay, so we've got 4 triangles, each with 180 degrees, meaning that our convex hexagon has a sum of 720 degrees. Well, if we look at the number of sides versus the number of triangles, we can see a relationship. In a triangle, there are 3 sides and a minimum of 1 triangle. In a quadrilateral, we've got 4 sides and a minimum of 2 triangles. In a pentagon, we've got 5 sides and a minimum of 3 triangles. And in our hexagon, we have 6 sides and a minimum of 4 triangles. So the relationship becomes pretty clear that the number of triangles, minimum number of triangles, is 2 less than the number of sides. And if we know that each triangle has 180 degrees, we can take the number of sides minus 2 times 180. So that is called the polygon interior angles theorem. The theorem says the sum of the measures of the interior angles of a convex n-gon, meaning n sides, is n minus 2 times 180, or the number of sides minus 2 times 180. Take a few minutes and answer the questions on this slide. What's the sum of the pentagon, the quadrilateral, and find the value of x in the trapezoid above. Go ahead and pause the video and then come back and check your answers when you're done. Okay, hopefully you got that in this pentagon, convex pentagon, we have 3 times 180, or 540 degrees. In our quadrilateral, we have 4 sides minus 2 is 2 times 180, or 360 degrees. And we know this is a quadrilateral, meaning it has 4 sides and a sum of 360 degrees. So when we add up all of the angles and solve for x, x should be equal to 50. So let's apply this. Find the sum of the measures of the interior angles of a convex decagon. We know a decagon has 10 sides. To find the minimum number of triangles, we're going to subtract 2 and multiply that by 180. That's going to give us a total of 1,440 degrees. In the next example, the sum of the measures of the interior angles of convex polygon is 2,340. Classify the polygon by the number of sides. So we'd like to know how many sides are in this polygon. So we're going to set that equal to n minus 2 times 180. We'll divide by 180 first, and 2340 divided by 180 is equal to 13. We'll set that equal to n minus 2. When we add 2 to both sides, we'll find out that this polygon has 15 sides. So we call this a 15-gon. Find the measures of one interior angle of a regular convex octagon. Well, if our octagon is regular, that means that all of the angles are equal in size. So we want to find the sum of all the angles for our convex octagon, meaning there's 8 sides minus 2 times 180. That's equal to 6 times 180, or 1,080. That's equal to the sum. If we know there are 8 congruent angles, we can divide this by 8 and figure out that the measure of each angle is 135 degrees. So this guy right here is 135 degrees. Try the next problem, and I will post the answer on Google Classroom.